Previously, we discussed the concept of energy band gap based on chronic penny model. Then we classified solids such as metal, insulator, and semiconductor. Here we apply Pauli exclusion principle which says each particular quantum state can only be occupied by one fermion. Electron is fermion. Then each quantum state can only be occupied one electron. So that's why there are many energy states. Then we fill the energy state by electrons. And each energy state is filled up by one electron. Okay, and it's filled up from the lowest all the way up to this energy. This one indicated by dashed line. Mu is chemical potential or Fermi energy. If it is partially filled, then we have metal. Electron could be conductive because the electron here, electron at the Fermi energy level, can move from one atom. Let's say there's an ion there's another ion, and they are repeated in the lattice site. Their distance is d. This distance is the lattice constant. They are aligned along certain direction, for example x. The electron will move around from here to here, and then here. We call it hopping. It moved from one atom to another atom. In this hopping motion, if electron here and another electron here, if the electron is moving to the other atomic site, their spatial position is overlapped. When their energy is the same, their spatial overlap cannot be allowed. So every time an electron is overlapped with another electron, and their energy should be changed, should be adjusted. So this electron at the Fermi energy, if it is meeting another electron, then this energy should be changed into something else. Okay. We know there's a vacant energy state here. So there are more energy states available. So when they somehow happen to be overlapped in space, one of the electrons should have different energies. So this is the basic idea of Pauli exclusion principle applied into space. Okay, and that idea of Pauli exclusion principle is applied into the formation of electronic energy state. And that's the way we can define Fermi energy. The same idea can be applicable into insulator and semiconductor. In the case of insulator and semiconductor, Fermi energy is in the middle of the band gap. Okay, in the middle of the band gap. Okay. Right. intuitive picture of band. This is not shown in the textbook. Still, it is okay. I'll just explain its meaning. If you read through these contents, it's good enough already. Electrons in inner shell of atoms. They are tightly bound to nucleus. So sharp energy levels of isolated atoms we have. Outer electron shells or valence electrons. We often call it valence electrons. Surely this is not related with valence band. It is different concept. Okay. Delocalized, which means the corresponding wave function spreads of a crystal, forming energy bands. So electrons in the outer orbit can be delocalized, means wave functions. Wave function is not simply localized near an ion. It is spread over space. That's the way we have energy band. And then we can have the gap between the bands. So we consider this periodic lattice potential. The atomic position is indicated by the dot, Here the atom emits the electron. Electron is moving around. So now the atom becomes ion, positively charged ion, so there's Coulomb attraction. So this solid line indicates the spatial variation of the Coulomb attractive potential. And in terms of intuitive picture shown on the right, for isolated atom between electron and nucleus. The nucleus surely have the positive charges. So there is a bonding between them, electron and a nucleus. Then there is a sharp energy levels as shown here: 1s, 2s, 2p, 3s. In the case of free atom, it means there is no another atoms. There is only one isolated atom, that is free atom, and we have electronic energy levels indicated by this horizontal lines. The energy levels listed here, 1s, 2s, 2p, 3s, will be discussed later on after midterm exam. The basic idea is isolated atoms will have discrete energy levels. Here we have a complex of two atoms. They are very close. When they are very close, electron can move around. Electron can move from one atom to the other atom. Then the energy state, let's say here it is supposed to be 3s. And now two electrons, their wave function should be overlapped in space, which is not allowed in Pauli exclusion principle. So their energy should be different now. So original single energy state should split into two. Okay. So when there are two electrons moving around between different atoms, then there is energy splitting. Energy splitting. You will see this phenomenon many times in material and device studies. Okay? This happens very often, actually. We see this phenomenon many times in research papers. You will see it. I can guarantee. So, two atoms, and then electrons can move around. Then energy state should split into two. So, for example, another very important problem is, previously we studied quantum well problem. Especially we learned the single quantum well with infinite barriers, and then single quantum well with finite barriers. Then let's say there is another quantum well. So quantum well 1, quantum well 2, but now they are coupled. For example, let's say barrier is very high here, barrier is very high here. So the potential U, here U is very large. U is very large. U is 0. U is 0 here. And this one, let's say it is very small. And when the barrier is small, then electron wave functions can pass through from one well to the other. Then electron from this quantum well and electron from quantum well 2, they spatially can be overlapped, because this one can move around and this one also move around. They happen to meet at the same position. In this case, original energy state should be changed. Okay? And we should have energy split. So original energy state, quantum well energy state that we studied from finite quantum well should split into two different energy levels. We see this phenomenon many times, even in such quantum well structures. Actually, it has been studied very well. So there are two different energy states in this case. Okay. So previously there were quantum numbers like n equal 1. Let's say we have n equal 1 state, and those n equal 1 states from quantum well 1 and quantum well 2, they split into two. This energy splitting. That's what happens for the case of two atoms. Okay. And when there are many atoms, like in crystals, then there are 10 to the 23 atoms cubic centimeter. So this is the density, atomic density, and there will be at least this amount of electrons. So electrons can move around the original energy state. now split into many different energy states. Okay? So this energy is very closely packed, so we cannot identify different energy states that easily anymore because they are too close. Then we call it band. So they are all related with actually Pauli exclusion principle. Right? This is the basic idea of band formation. Energy bands. By using Schrödinger equation, we could induce band gap based on Kronig-Penney model. In reality, the conduction band minimum and the balance band maximum points are crucial for electronic transitions and interactions, and they have specific angular momentum quantum number as shown below. You will study the angular momentum quantum number later on. Roughly speaking, previously we see 1s, 2s, 2p, 3s for isolated atoms. Isolated atom means, let's say we have a ion here, another ion here. In crystal, they have separation defined by the lattice constant. This lattice constant is actually pretty small, smaller than 1 nanometer. Okay, but when they are separated very large, for example, like more than like 100 nanometer, for example, then atomic bonding we can ignore. Okay, then this atom is isolated, we can say. Then we have this discrete energy levels of electrons. And 1s, it means total quantum number is n. It is one total quantum number. Or you can say principal quantum number. You will learn it later on still. It's okay if we don't know the details, but you will see it. And S is the indication of angular momentum quantum number of 0. L is the angular momentum quantum number. Here. Angular momentum quantum number. Here S, so it is L equals 0 state 2. Yeah, total quantum number is 2. And total quantum number is 2, then there could be another angular momentum state. L is 1. So those two cases are when total quantum number is 2. And then 3s. Total quantum number is 3. L is 0. When n is 3, actually L could be 0, L could be 1, L could be 2. When L is 1, we call it P. So there could be 3p state. When L is D, we call it D state. So there is 3D state. So depending on the number of electrons in that atom, we will feel the energy state from the lowest. Okay. Then 1s state, there are 2 electronic energy state. 2s, there are 2 energy states. Actually, those 2 are actually related with something called spin quantum number. You will see it later on. 2p, actually there are 6 energy states, okay, with different spin configuration. 2. So in this case, actually, this 2p has some different spin quantum numbers. It's rather very complicated, but roughly speaking, let's say we have 6 electrons assigned here. The details you will learn in later on. Such as 6 electrons, 2 electrons, 2 electrons. There could be 2 electrons. So in this case, total electrons are 12. Okay. Yeah. Anyway, those are actually atomic states, right? And here in this figure, this is energy, and this is the separation between atoms. When R is very large, goes infinity, then it is isolated atomic state. There could be S state and P state as shown here. We see 2s, 2p, 1s, something like that. So when they are isolated, we could fill the energy state with electrons, and let's say there is S state and P state. When atoms are very close with each other, then there should be band formation in crystals. And let's say the average distance between atoms in this case is R0. Then there is band formation. This is band. The low band is called as valence band. Higher energy band is called as conduction band. The conduction band edge here, this point, valence band edge or valence band maximum. We can also say conduction band minimum here. Their distance and their separation is band gap Eg. This one related with S state. This one related with P state. That is actually related with that concept of energy splitting. Okay. So the minimum of conduction band usually behave like S state. Maximum of valence band behave like P state, and angular momentum is 0 here, and angular momentum is 1. Their angular momentum separation, delta L, could be plus minus 1, and there's a transition between conduction band and valence band. And this is actually the same with angular momentum of photons. Okay. The photon should have angular momentum of 1, but if its direction is opposite, then it could be described based on -1 or sometimes +1. So the absolute value itself is important. So photonic angular momentum quantum number is actually 1. When there's S state and P state, and their transition between them always related with photon emission, because their angular momentum selection rule is satisfied. Okay, you don't need to know the detail, but eventually you will study these concepts in many semiconductor materials. Okay, because this is the basic idea of the electron. Then photon. It could be like a conversion, you can say. Conversion. Photon could be replaced by electrons. Electrons could be replaced by photons. Then we can say conversion. Okay. Or we can also say electron-photon coupling. Okay. Those concepts can be described based on this intuitive picture. Okay. Those are actually important research topics. Okay. Electrons and holes. We know electrons very well. Okay, right? Do you know holes? What does it mean? In semiconductor studies, we always consider electron and hole. Okay. Usually at the same time, because when you have conduction band and valence band, we drew down those parabolas. Then y-axis is energy always. X-axis is k, the wave number. Okay, there's separation between band, always indicated by band gap. This is the basic idea of describing semiconductors. And here, valence band is fully filled by electrons. Conduction band is mostly empty. If the electron from here is excited into conduction band, and there's a vacant state of electron here. Those vacant state of electron is called as hole. Okay? When one electron is missing and one electron is now in conduction band, then you have negative charge here, negative charge here. When electron is missing, then we call it hole. Then now we have positive charge. So missing one electron is equal to one positive charge, named as hole. That's the idea of semiconductor description. Okay? The reason behind this is when you consider the current density J in electromagnetism class, J is defined as charge minus E, so electronic charge. So this is the current generated by electron. Okay, let's say there are many electrons, so we need to consider the density of electron, N is the density of electron, minus E is the electronic charge, V bar is the average velocity of electron. V bar therefore is N is the density, V is the volume, and these are the number of electrons. So V is actually the number of electrons. Let's say it is like large N. Then to calculate V bar, we need to sum the velocity from the first electron to nth electron, like that. And then we put this into here. Then yeah, this one subtract each other. Then we have this one. This is the current density. And if we consider the band, let's say this is the valence band, this is energy, and kx is the wave number along x direction. If it is fully filled by electrons, then we see that the J should be 0 because look at this. Actually, we know momentum P is actually h bar. Okay, here we only consider one-dimensional movement. And this one is actually same with m and then v. So velocity is proportional to k value, right? So and here the dispersion or energy k relation has the symmetric structure, okay, from the center of 0. So right hand side, left hand side, they have symmetry. So if you have the positive value of v, there should be always negative value. Okay, so that's why for fully filled state, J should be 0. But for fully filled state, except for one electron state S with velocity Vs is missing, and the J should be described like this. Now S state is missing. Okay, so this one is just the same. We sum all the electrons except electron in S state. Let's say its velocity is Vs, then we should subtract by that amount. And here we see that this one was 0, so eventually we have this. So J is E over V multiplied by Vs. And here is the charge equal to single positive charge. Okay, so this is the current generated by a single positive charge, right? So total current of all the electrons in the band with one vacant state is equal to current with one positive charge. So that one positive charge, and this corresponds to the missing electronic state, and we rather describe based on fictitious particle. It is not realistic, but if you presume there is a hole, instead of missing electron, we just consider there's a one positive charge. We call it hole. Also, that missing electronic state could be at the center here at the k equals 0 point. Then we think that okay, k equals 0, if momentum, k is 0, then v should be 0, right? But in realistic devices, there is always electric field. So electron or any charge should be accelerated. So Vs easily becomes non-zero in devices. So even though it is supposed to be 0, it is usually externally assigned to certain velocity value. Okay, now we should have J value then. So missing electrons is now named as holes. Okay, missing electrons in the valence band are described based on the concept of holes. Okay. This is actually taken from undergraduate semiconductor class. For example, Niemann is famous and easy textbook for semiconductor materials and devices. It is offered in third year in most of the universities. If you read through chapter 2 of Niemann, then you will find the same concept. those are actually closely related with the concepts of conduction band and valence band. That's why we are dealing with these concepts. Okay. Right. Because this is somehow designed for applications in the end. So that's why I introduced the concepts of electron versus hole here. And then effective mass. It is not mass, it is effective mass. Probably you heard of this. Effective mass is the mass in the semiconductor materials and also general crystalline materials. This is actually very important. In crystalline materials, we saw there are bands, conduction band and valence band. We see band structure. The most simple band structure was conduction band and valence band near K equals 0 point. In semiconductor research papers, you will see these band structures so many times. They are actually not just single band, there are actually many different bands. We often call it valleys. There could be different conduction band and different valence band depending on different K values. But we will ignore this part for now. We only care about K equals 0 state. And K equals 0 state is actually most important in semiconductor applications. So, in this case, we can consider effective mass. We know energy band is a function of wave vector. We consider energy K diagram. Energy wave vector dispersion, yeah, same meaning. Dispersion, band diagram, band structure, they have the same meaning. And let's say this band structure could be expanded in terms of K, right? So, for example, here in this figure A, let's say the minimum value is E0. And then we expand the energy values as a function of K, then first term dk, then multiplied by K, but we consider values near the minimum, which is the most important point in semiconductors, because it is minimized, the derivative should be 0, and the next term is second order derivative, 1/2 multiplied. But that's the idea of expansion, right? So d square e dk square at k equals 0 point and multiplied by k square. Alright, so this is 0, and let's ignore this constant value. We only care about this k square dependent term. Then look at this. So if you have the kinetic energy term, as we know, it is always like a p square over 2m. That is the kinetic energy term. Okay, in Hamiltonian. Okay, so this is the p square over 2m. In wave picture, this is same with h bar square, k square. Right? So let's ignore this part for now. Sorry. Let's ignore this part. So this is the kinetic energy term. Okay. and there could be some potential energy term. Okay, let's ignore this part. Minimum energy term, we ignore this part. And then others are said to be the same. Then you will induce effective mass, okay, by comparing this left and right hand side. Then you will get this, okay, and this is called as effective mass. This is actually very important definition. So effective mass, let's say we consider electron, for example, is equal to h bar square over d square e dk square at the point of k equals 0. So for these three figures, A, B, and C, we can consider effective mass. We see that this is the second order derivative, and here if we take the derivative, it's minus value, which is pretty large, and then we take the derivative here, positive value, pretty large, and then we take the second derivative, means their gradient, okay, minus 2 plus, it should be positive and it should be very large, okay. If this one denominator is very large, then ME should be very small, right? Because denominator is very large. Likewise, if we're slowly changing, then this is minus, if we take the derivative, and it will have positive value here, minus value here, if we take the first derivative, I mean d dk, okay, minus value, plus value, but their amplitude is pretty large, pretty small, and their change is not that large compared to A. So it means if we take second derivative, d square e dk square, it's actually rather small, okay. If it is small, ME, the mass is large, okay. In this case, actually, if you take the derivative is positive, take the derivative is negative, then second derivative should be minus, right? So actually this is considered to be whole, okay? So in this definition, the mass of whole is negative, okay? It is just mathematical definition, but mass cannot be negative, so if it becomes negative, we just recognize it is whole, okay. And then in research papers, we just use positive value, okay. So it is mathematically negative, but in physical description of whole, we use positive values, okay. So if there are anything unclear or you are curious about, then leave the comments. Alright, and then we can consider direct versus indirect semiconductors. Direct band gap semiconductor, the valence band maximum and conduction band minimum both occur at k equals 0 point. The strong optical interactions are observed, for example, absorption, emission, stimulated emission, eventually useful for laser action. An example is gallium arsenide. Gallium arsenide is the direct semiconductor whose band diagram is shown here. Band diagram, dispersion, band structure, they have the same meaning here. So conduction band minimum is here, valence band maximum is here. They are occurring at same k equals 0 point. On the other hand, indirect semiconductors such as silicon, valence band maximum is here, conduction band minimum is here. So in K space they are separated. So minimum in the conduction band occurs not at K equals 0 point. So optical transition is strong, optical transition is weak, because there should be always momentum conservation, and this K is proportional to momentum. If we multiply it by h bar, then that is the momentum. Okay, and K equals 0 point means electronic momentum is very small, near here. So let's consider momentum of electron. It's very small. Okay, near when K is near 0, and photonic momentum, photon momentum is actually very small. Here photon means surely the we consider h bar. K, here K is the photonic wave number. Then you should consider 2 phi of lambda. Lambda is wavelength of photons, and in our conventional range of photons, for example, visible range, the wavelength of photons usually on the order of like 700 nanometer. And this one is actually a very large value, because when you draw this curve or Venn diagram, then the maximum of K value, K can reach only up to phi over lattice constant D. Okay, that's the maximum value of K. So this D is actually lattice constant. Lattice constant is much smaller than 1 nanometer, usually on the order of 0.5 nanometer. Look at this one and this one. So photonic momentum said to be extremely small. Look at this. Yeah, extremely small. If you compare this one and this one is much larger in terms of K value. This one, right? So now we know that photonic momentum is considered to be very small compared to the electronic momentum. And in this case of silicon, because electron and hole, they are separated in K space, and this value is too large. And when electron is converted into photon, there should be momentum conservation. So electronic K value should be converted into photon's K value. But photon cannot have this large K value. Photon cannot have such large value. So the transition is extremely hard. Then it doesn't emit any light. Actually, it could. So there should be additional interaction with phonon. For example, this electron will emit phonon. So phonon momentum could be very large actually. So it emits phonons, then goes to lower energy state near here. Emit the phonon and goes to here. And this electron now again, goes to the lower energy state. So phonon should be emitted so that there is any light emission in the case of silicon. Actually it happens, okay? But yeah, the efficiency becomes much smaller. Okay? Now we revisit to the concept of density of state. So, energy in 3D crystals, considering periodic boundary conditions, and the energy is quantized, and here K value is quantized. Let's say we have crystal whose length scale is like Lx, Ly, Lg, and electron is confined within the box. Previously we solved the one-dimensional potential problem with infinite barrier, and that scale is supposed to be same now with the Lx. Previously we set this to be same with A or D in one-dimensional quantum problem. And KBRs are confined within here. It cannot be existing outside, so potential outside, so let's presume that it is infinity. So KBR is confined within here. That's the case of crystal with this volume. Then related K value is shown here. Okay, K value will generate these values. Okay, it is confined depending on integer nx value. Nx is the quantum number defined along x-axis. Likewise, along Ly, along Lg, we can define. Okay. Actually, this is what we learned from solid state physics. We don't go into detail, but we intuitively understand the meaning of this structure. The meaning of this structure is K value is quantized and scale is fixed, and electron is confined within certain scale. Then K value is fixed and discrete. Those three K value, Ky and Kz, should be discrete now. So that's the way we have quantum numbers assigned to nx x-axis and y-axis, and this should be ng. I'm sorry about that. Should be ng. It should be also Lg. Okay. Then we can consider the concept of density of state in 3D. To know the detailed mathematical procedures, actually we need at least 1 week. But, to consider those mathematical details is not the purpose of this class. I will just consider how we how we consider the applications, okay? How we find the applications. So we'll just accept some of the important topics here, right? And the density of state is defined as shown here. Okay. So d, dk, then we eventually will see that the density of state is proportional to square root E. This is what we learned from undergraduate classes. So the meaning of this density of state is it describes how many states are available in the system in an energy interval between E and E plus TE. Okay, And when we extend this concept into the case of semiconductor should have band gap. For example, energy can exist above EC and below EV. Valence band energy, conduction band energy, and their separation is band gap. Okay? That's the semiconductor structure. There's nothing in between. Okay? That's why it is band gap. So in the case of semiconductor, we should change this like this. The energy E doesn't exist below EC, so that we change the change E by E minus EC. Okay? The square root E could be real only when the exponent E minus EC should be only when it is positive, right? So E should be larger than EC to be real. Okay? So GE exists only when E is larger than EC. That's the concept of semiconductor. Okay? So without semiconductor concept, density of state in 3D is increasing with square root E. And then if we apply that into semiconductor materials, then no energy state between conduction band and valence band. G, the density of state is increasing from here with square root E function. So square root E minus EC is increasing like that. And here we also have the energy state below the valence band maximum point. So here we should have EV minus E. Okay, and it is multiplied by additional parameters here, and that parameter has effective mass term. This is effective mass. This is also effective mass. Okay. Another important concept is occupation probability in each state, consisting of density of state. So we consider density of state GE, right? Then this describes the number of quantum state. Okay, this describes number of quantum state. At certain energy value E, right? So there are this many energy state, then we feel that energy state by electrons. Okay, and when we feel that energy state, there is also probability of feeling that state. That is distribution function. Okay, and this is actually, in some sense, a simple concept when you consider number of electron in certain material. It should be like, let's say we consider certain energy value, okay, then there are quantum state like GE, and then there are occupation probability, okay, to feel that energy state. So it should be formed like this. A certain energy value, we can consider electron density, then F multiplied by G. Okay. And that's why we also consider F. The probability to feel that energy state. So determines the occupancy factor of electrons and holes in an energy with energy E. It is called as Dirac distribution function. Fe is equal to 1 over 1 plus exponential function, and the exponent is E minus EF. EF is the Coulomb energy. Sometimes we describe it like mu, chemical potential sometimes. And KB, Boltzmann constant. T, temperature. Okay, so if we draw this curve, well, as a function of energy, so epsilon is energy here, same with energy. So this is actually proportional to energy. Okay. KB is the Boltzmann constant, but basically x-axis is represent the energy increment. Okay, then we see that this F at very low temperature, for example 10K, is available temperature in laboratory, then it is very stiff. Okay, and this one we see that this value is actually interesting because look at this. When F becomes half, it means this one should be 1. That's when energy equal to Coulomb energy. So actually this is when energy equal to Coulomb energy. So more exact definition of Coulomb energy at finite temperature is when probability distribution function becomes half. Okay. Well, and then as we increase the temperature, the T increases, so this exponential function changes slowly. Okay, and T becomes large, so 50K slowly changing, 300K slowly changing. Okay. We see that for low temperature, for example 10K, F, or you can describe based on the wave number, but let's just describe based on energy. So energy and K, they are correlated with each other, so sometimes people use K dependent description. Let's consider energy dependent description here, Fe. We see that when the energy is smaller than EF, this side probability becomes 1, and energy is larger than EF, probability becomes 0, this side. We see that. And then for larger temperature, T is increasing, then the original step function like shape is smeared out. It's slowly changing like this. Slowly changing like this. The temperature is very large actually. T is very large. and also E minus EF is large enough compared to thermal energy, then this one is large. So when we compare 1 versus exponential function is very large, so we ignore this part. That's why we have this simple description. Then we call this as Boltzmann distribution. Okay. Mostly we call this as Boltzmann distribution. All right. So that's it for today's class, and there's a homework problem, homework number 3. Induced equation 3.31, and next week we will consider tunneling problem, but midterm examination will only include up to this point, okay, particle periodic potential. So even though we will study tunneling problem, it will be excluded from midterm examination. Okay, that's it for today.